I'm David Booth. Today's webinar by Dr. Parsa Mirhaji is one in a series of webinars about various aspects of the Yosemite project. The Yosemite project is a collaborative effort whose mission is to achieve semantic interoperability of all structured healthcare information. It articulates a roadmap for achieving interoperability based on RDF as a universal information representation. In today's webinar, Dr. Mirhaji will discuss work that has been going on at Montefiore Health Systems and Albert Einstein College of Medicine to build and use a semantic data lake based on W3C standards, best practices, and knowledge representation in healthcare. This work helps to demonstrate what can be achieved through the use of RDF as a universal information representation for healthcare data. Welcome, Dr. Mirhaji.
Thank you very much, David. In the interest of time, I'll start with background and walk them quickly so we can get into the introduction of SDL. Very quickly, this is the ecosystem in which Montefiore and most accountable care organizations operate. We have a lot of patients that are frequently interacting with digital media and generating a lot of data about themselves, their behaviors, and their environment. Frequently, they come with some devices that are attached to them, like Fitbit or Apple Health Kit or other technologies that collect a lot of biomarkers from their heart rate to their sleeping patterns to their mobility and a lot of other information that is generated by them living their lives, and that's very important. Many patients come with their genetics tests done and a lot of genetic information about themselves and about their family members, pedigree of histories of many diseases that are now relevant in our understanding of the patient's phenomena. And sometimes we give them devices that they take home and collect a lot of data about their health conditions at home. And this all happens outside of the hospital, but when they enter the hospital, we interact with them even more broadband. We collect a massive amount of clinical data using our EMRs within the EPIC system. We tie them into sensors, detectors, devices, monitors in different clinical settings inside the hospital that collects a lot of interesting physiological data about these patients. We have lab systems that create biomarker data, waveforms that we generate, images that we collect, pathology information down to the point that patients are dead, and even after that we collect a lot of information about these patients within different departments, medication data. As a accountable care organization, we have a massive care management organization where nurses and practitioners interact with the patients after they're discharged from hospital to coordinate their care among multiple participants on delivery of care process within health homes or in a nursing home or within patients' their own settings. We generate financial data, interactions of our institution with the payers and the legal liabilities and lawsuits and the risks that we take by interacting with patients. These are all kinds of information that we collect. We maintain an inventory of all of the devices and their conditions, their quality, their calibration that are all important in an understanding and providing quality care and reducing, not only reducing the error, but also being in compliance with some of the regulatory aspects of the delivery of care process. Our interaction with our own staff, creating the financial environment where we can pay them and promote them within their career, and the relationship that they have with our institution, management of our assets, provisioning for utilization of those high-value assets like our imaging facilities, our chemotherapy seats, down to the level of parking slots that we have available so that we can optimize utilization of these resources within the institution, and log files of all of these systems as they interact and transact in a daily manner. As an example of why these log files from These systems are important. I can reflect on one of our projects that was looking into clinical errors in prescribing wrong medication that were due to physician looking into more than one patient's data at a time in their screen. And the only way we could actually discern how many windows did the physician had open when they were doing the medication, what were the content of those windows, and how did it relate to activities that they were conducting at the time within each one of those windows, and whether or not they had anything to do with the clinical error that we are tracking was only achievable if we could link between content of the database and content of the log files to create to piece together a history of events and look into coincidence of those things. So this is basically the big data environment that Montefiore operates, and the basic question is, so what is the characteristics of the system that can help us deal with this copious amount of data and information that we are generating consistently. I'm sure every system, every organization has a level of sophistication in terms of building infrastructure to ask and answer questions like the ones we are interested in. I was trying to categorize those technologies, and this is a very naive way of looking into the information space and the tool sets that are operating in those. The point I'm trying to make by this slide is that there are many categories of data, and some of them are bigger than the others. Some of them are inside the hospital or inside the institution. Some of them are outside, and there isn't really one easy way of creating a single source of truth so you can reliably and consistently access data and interpret it among multiple use cases. Historically, technologies like I2B2 or OMOP and some private sector technologies like CLG has been developed to create a self-service and some economy of scale for practitioners inside the hospital with a focus only on the EMR data, things that are clinically motivated when the patients are interacting with the health systems. Frequently, most of the larger healthcare systems have invested in building enterprise data warehouse that does cover almost exactly the same area, plus administrative and financial data that would be relevant for the operational support of the institution. But there isn't really a robust infrastructure that I know of that can cover the entirety of this space in terms of dealing with the real-time data generated by those devices, images, free text, data from panomics, connectivity to national networks, and most importantly, linked open data, the massive amount of heterogeneous data that is outside of the institution, very relevant to the practices that we have inside the institution, but not very straightforward in terms of putting it into an analytic framework that is ready for analysis. And our notion of semantic data lake is basically an idea about how we can create a single source of truth for accessing and delivering these varieties of data into our both research setting and operational setting consistently. Another way of looking into that dilemma is by just looking into the maturity model that organizations should evolve into if they want to really become a data-driven learning healthcare system. The step one, obviously, is just to aggregate data, fragmented data points, and put them in some central repository that would essentially enable basic reporting. So you can go there and create some dashboards for executives and some ways of creating views to those data. The next level would be basically scale out, which is do the same but in much larger scale, covering internal reporting and external reporting automatically. And that automation will require a lot of investment in building standards, terminologies, harmonization methods, and registries with consistent and standard definitions that everyone can understand and subscribe to. And that can become the basis for building automated mechanisms to leverage that for many different use cases. And that is where, once this is done, scale and the data has been democratized and delivered in the enterprise, that's when the culture of using data as part of your workflow process will emerge inside the institution. And then you can expect that you can build facilities that can really do change the organization systematically. For example, you can start building waste reduction models and or reducing variability in delivery of care processes that at the end of the day, these efforts are the ones that will make a return on our investment in building the data infrastructure and actually utilization of EMRs realized in large institutions. And anything above that is these are the value-added services that you can expect from investment in analytics, building characterizations, population health management models, predictive models that are critical and the core enablers of accountable care, managed care, or value-based or quality-driven healthcare system. That's basically the healthcare reform. And the underpinnings of all of those are these kinds of infrastructure that we need to create. And of course, these days, everybody is talking about learning healthcare systems, precision medicine, which is application of linked open data and genetics in making personalized interventions at the individual level. The point I'm trying to make with this slide is that, yes, it is an incremental process, and each milestone adds value of its own kind, but it is not sufficient just to create a massive data repository. Data is only one component of the solution. We need consistent terminology management, consistent metadata management, consistent knowledge management, and linked open data for this vision to materialize. And again, the question is, what is the construct? What is the architecture that can be used to scale in data integration, as well as enable terminology management, metadata management, modeling, and knowledge management, and linkage to informational assets, both information and knowledge assets outside of your institution. These two ideas are the ones that actually have motivated design and implementation of Semantic Data Lake. We have really thought about architecture that can help us navigate this maturity model. I'm not making claims that we have done it. It is complete and it is ready to use by everybody, but I can claim that for each one of, or for most of these layers, we have competencies that we have developed that can demonstrate that Semantic Data Lake is a appropriate kind of architecture to enable institutions to go in that direction. So what is it that we have done? It is basically an architecture based on principles of big data analytics, Internet of Things, and cognitive computing. It is a graph-based technology that is built on top of, technologically on top of semantic web, and utilizes HDFS, Spark, and graphics as its core technology to distribute processes and integrate data, manage memory efficiently, and scale out and do analytics both in memory and enable transactional data management in parallel possible. So you can consistently collect data in real time as you are running the analytics on the infrastructure. It has technologies specifically directed as towards biomedical field, enabling consumption of biomedical terminologies and ontologies with very robust URI level security and authorization and provenance. facilities. I'll show you a little bit of that. We have made sure that we are capable of digesting both structured and non-structured data, mainly clinical, but still very integrated approach to clinical text understanding, as well as data integration of structured data. We've built specialized temporal analytics, geospatial analytics, and machine learning algorithms that are now inherently integrated to this platform, so they can be invoked and scaled on top of the large data set. And it's basically a multi-institutional collaboration between Montefiore, Franz, Intel, and Cisco. So what does it look like? I'll make some assumptions as I move forward with this. One of them is that I do not need to speak of what is a graph representation, what is RDF. But I'm assuming that the audience knows a little bit about these things, but I'll keep it fairly non-technical. I'm trying to open the hood and show what is underneath. The principal design architecture that has enabled Semantic Data Lake is to understand how a single data point is represented in Semantic Data Lake. Obviously, being semantic, it is linked to a term or an ontology that defines what that data point is, and a literal representation of that for human use. For example, I'm just reflecting on one data point here, which is about a medication, which in this case is amoxicillin. But then it's also linked to the term that was used by the source system to reflect on this. If the source system has used a coding system, for example, a NDC code to represent this amoxicillin, we represent that too. So you can assume that our system has a library of these terminology systems to link to. And if we normalize to represent this term in a standard way rather than the way it is represented in the source system, we have also a link to normalized or the standard representation of that. So by now I know I have amoxicillin for the patient and two code sets that defines it, and each one of those code sets, by the nature of being driven from some knowledge base, are bring in a lot of metadata and knowledge about them. So you can actually look into RxNorm to see the classification and the hierarchies associated with these medications, or within NDC you can look into makers and packaging of these medications. If we have made any transformations, the rule of those transformation is associated with that term. What applications in what use case or role scenario can access this data point is also attached to that data point. We allow different user communities to annotate their data the way they want. We have a generic way of annotations, but we also enable people to annotate their data however they want. We have an annotation framework which enables, for example, if in the side a use case requires linking of this data point to FDB, First Data Bank, because there are a lot of meta information and ontological representations within First Drug Bank in terms of the chemical structure and the indications and contraindications of the medication that might be relevant for the analysis. We enable that. Extensions of the ontology or linkage to other ontologies, if it is necessary for the analysis, we enable that. Every single interaction in the system is timestamped, so every data point comes with a timestamp on when we did the transformation, so you can build a history of those, and we have a very granular representation of every single data point as well. Metadata about the lineage of this information. What was the series of ETLs or data transformations that has happened before the data has been represented in RDF format is also linked. So you can actually look into the source information coming from EMR, going into Enterprise Data Warehouse, and coming to the SDL, and how many transformations has happened, what was the original data representation at the source, and what was the intermediate representations before it got to Semantic Data Lake is also linked. If we use this data point in any analytics downstream, results of that analytics driven by using this data point as an input is also linked to it. So we can, by looking into any data point, we can see in how many different places this single data point has been used and what were the results associated with that. And of course, every data point is linked to another. For example, in this case, this amoxicillin prescription is perhaps related to an encounter in which this medication has been prescribed. So that was anatomy of one data point. Let's see how multiple data points connect to each other and become Semantic Data Lake. Another example from chest X-ray, of course, codings used to represent this in multiple sources, and all of those metadata that I mentioned is there for an X-ray. We can use this annotation to link it to, for example, the cost structure of this X-ray for research setting or for industry-sponsored clinical trials or paid by Medicare. So you can actually create multiple cost structures for that one service and say if this is done by Montefiore, this is the price. If we charge it to industry, this is the other charge, duration within which that charge is valid. And if we are billing this to Medicare, what is our contract? So the terms of the contracts, multiple different ways of creating invoice for that one service can be annotated by financial people. A clinician may annotate something else, but this is basically how you start contextualizing every single data point in our setting. You can add calibration, for example, information about devices used and the schedules available or the time slots available for that device that took this image can be also part of the annotation. So you can actually use this annotation framework to manage a lot of meta practices around in every single data point. Now that we have that X-ray, you may want to say what was the person that X-ray was taken, and what was the address of that patient that we did that X-ray for. And the address itself can be annotated by geocodes, longitude and latitude of that, to the census tract information and household information. So how large was the house? How many bedrooms does it have? What's the neighborhood like? What is the average price of a square foot of a house in that neighborhood, in that census tract? So you can basically start implementing linkage between the socioeconomic constructs with the patient data here. So we got that covered. We can link it to the encounter in which this happened, diagnoses made for that, and then you can collect a analytics. You can run a predictive model that would predict what would be the readmission risk for this patient based on everything you know about this patient, the clinical representation of the patient, neighborhood this patient lives in, qualities and costs of providing the service for the person. You can use all of this analytics information to create analytics and risk scores for the patient. You can link it to providers, and then you can bring information that you have about the provider to better understand these practices, facilities in which these services are provided, and then you can link it to another higher level analytics, which calculates what is the distance between the place this person lives and facility within which this person is being cared for, and what is the relationship between that and the readmission risk of the patient. So this is basically how our overall metadata / knowledge / linked open data management framework links together to create a consistent representation of health data. And as you can see, it is a very iterative process. It is the same architecture repeating itself to create more complex constructs that once you put it together, it really becomes a community and population-based data set that evolves longitudinally. For every single data point, there is a knowledge base that further contextualizes that knowledge base, and linkages that one can provide between that knowledge base and outside sources to annotate these single data points further, or analytics that you run outside, and you can link it directly to the patient data. We have also a mechanism you probably noticed that we call it analytic tapestry, which is a consistent process of returning results of analytics every time that it happens back into the semantic data lake and closing the loop on collecting these information as part of our larger vision to build a big data environment. This whole construct is what we call our evidence generation paradigm, which brings to bear on data that we can bring in, annotate, contextualize, and analyze, and learning that happens within the system that can be returned back into the system. So that was overall overview. Now let's take a look a little bit into the architectural components that I briefly introduced. Of course, we have a knowledge base. That's the core brain, basically, behind the system. It is a knowledge base of, currently we have over 1.5 billion triples only in the knowledge base. A big part of it is geographical information from census and other socioeconomic data, but the entirety of the UMLS, 182 vocabulary systems from UMLS, is integrated into it. The entire OMOP terminology is there, clinical trials, OMIM, drug bank, and several other knowledge sources, First Data Bank, and those are also part of this. And its core representation, its knowledge representation framework that is being used is Simple Knowledge Organization System, another W3C standard that uses semantic web and RDF as a way to create thesaries, meta-thesaries, and mashups between them. So it's a huge mashup of all of these things. Very quick introduction to its structure. As I mentioned, it's an extension to SCOS. So you can expect that all of those SCOS concepts, concept schema, labels, and label structures, semantic relations, all of them are there. We have taken those SCOS concepts and extended that to create an ontology of biomedical vocabulary by aligning it to UMLS. So we have basically translated UMLS to SCOS and transformed the entire UMLS into SCOS representation, complete with the semantic network and semantic relations that are incorporated in the meta-thesaurus part of the UMLS. And then each source vocabulary inside meta-thesaurus is also turned into SCOS and linked to the meta-thesaurus. So this way, you can look into the meta-thesaurus information from the quiz perspective to see all of the ontological relationships between a concept like abdominal pain. But then you can change your focus from the meta-thesauri level to specifically SNOMED's perspective, or MEDRA's perspective, or ICD-9's perspective of these phenomena, and basically narrow down on a very specific part of the knowledge base that you would believe has the information you need to make the analysis. In the side, we have also linked that to OMOP. OMOP is a subset of UMLS, which is being curated by a big data analytics group called Odyssey, especially to enable observational research and data science using clinical data from EMRs. So it is a lot more cleaner, more a high quality terminology that is validated across several large-scale analytic use cases to consistently represent clinical findings. So we have made the linkages, and that is basically the internal link point for all of the biomedical concepts within Semantic Data Lake. And once we link to OMAP, we also are linked to SNOMED, to LOINC, to ICD, and to the thesaurus. And we can basically bring everything and make it queryable. If you want to look at it, this is how it looks like. In the left-hand side, you would see the semantic network, which creates a very simple but useful classification of these terminologies within the network, and meta-thesaurus information like synonymy, definition of the concept, preferred labels, all of the mapping between multiple terminology systems. They're all consistently represented. I made a very quick remarks on its composition. This is the current state of what it is. Without census tract, it is close to 600 million, almost 500 million triples. With census tract and geocoding data, it is more than 1 billion triples. So if I want to look more closely inside it, if you just query for something like diabetes mellitus, you will see diabetes mellitus in multiple different representations from multiple languages, as well as which coding schema in what version has been used to construct this representation. You can see that in the left-hand side. You see tracing of each one of those labels to the terminology system, version of the terminology system, code used within that terminology system, and version of that terminology system. So you can trace these concepts. In the left-hand side, you see the semantic relationships according to the meta-thesaurus, relatedness, broader, narrower relationships between the concepts, such as polyneuropathy and different representations of neuritis and peripheral neuralgia and everything else. In the right-hand side, there's taxonomic relationships. Building a hierarchy of terms is possible by navigating different parts of the graph. And once you have these interconnectedness, you can do pathfinding queries. This is one query. This is just an illustration of what is possible now that you have a knowledge base like this available within the system, that shows the value of having knowledge bases like this one. This query, you can actually start reading it. It's very intuitive to read. Is saying that for a medication that find medications that are indicated or contraindicated in diabetes mellitus. And for those that are contraindicated, find their mechanisms of actions. I have not selected all of the medicines, just a few of them that are enough to illustrate the case. And I will ask the system, now that I know what are the contraindications and indications of different medications for diabetes mellitus, for those that are contraindicated, see if you can find a pathway based on the mechanism of action. This will, so all of the red nodes in the right are basically a result of a search algorithm that has looked into the mechanisms of actions and their pathways to see if there are any common pathway between any one of those nodes. And you can immediately see that, for example, the adrenergic agonists are common pathway between these two mechanisms of actions, and there is a common pathway around the G protein linked receptors across all of these medications and all of these mechanisms of actions. So there's a very quick illustration of how these ontological mashups can give you further insight that is not possible to gain without having these knowledge bases. Or you can ask questions such as, given a medication, tell me everything that there is to be known about this one medication. And as you can see, we have all of the packaging, formulation information, dose form information, indications, contraindications, and mechanisms of actions of this one medication coming from multiple sources in one single graph. The nice part of this is that once you link it to patient data, then you can really have a lot of insight about patient data by having the knowledge base associated with every single data point. Here we are looking into one single patient that had a peanut allergy diagnosed in an encounter. So this is basically showing there's a person that has an outpatient encounter. Within that encounter, we had a diagnosis, and that diagnosis was allergy to peanut. Allergy to peanut is linked to the ICD code of the allergy peanut based on ICD-9. But that one linkage is enough to connect it to the entire knowledge base of how these allergy to peanut is classified within different representations. You can actually see that we have now gained insight about this one code. Normally, this is the only thing you see in clinical databases. This is where the buck stops in relational representation of a data warehouse. But now we know these are the many different ways that allergy to peanut may be represented in a clinical database. You can build a lot of interesting NLP algorithms based on this. From OMOP, you can actually solve causation information, what causes it, and the disease classification. I can, at any given time, I can ask a question such as, what are the allergic disposition, how many patients with allergy to a substance are there, and how many of them have food allergies. These queries are not possible because of these linkages. And then a more robust query based on those path-finding features that I showed you would be, take one patient and say, find any patient that is similar to this patient and rationalize it. Tell me why those people that the system finds as similar patients are somehow related to this patient. As you can see, based on a retinal detachment event in this individual, we have found 4 other individuals with different forms of the retinal detachment that fall into the same category of disease. Therefore, system believes they are similar. And again, this is impossible without having those knowledge bases linked to the data and algorithms that can navigate the data space, information space to create these results. As I mentioned, our representation is a highly iterative, very well organized and structured, although it is a graph, but it's a very structured graph of its own. This actually shows you that if you want to change the lens from graph to, let's say, a third normal form in relational schema design, you can actually create a third normal form view of the graph of the patient information in the Semantic Data Lake. I'll speak a little bit about the consequences of having this, which is the ability to, in real time, create just-in-time data marts out of graph based on results of a very complex graph query that would be persisted in any relational database for people that want to see information in relational, but can't harvest that from graph because they're not familiar with either the structure or the technology to be effective in that respect. So this shows one patient, their encounter, diagnoses within that encounter with the timestamp, the types of the diagnoses and encounters, and what was the diagnosis made within that encounter. Very structured, and this can be transformed into a comma-separated file or a relational representation very quickly. I talked a little bit about linkage between data and knowledge. Here I'm showing the metadata management, some of the facilities that enables tracing and tracking of the data within technology constructs. As you can see, every single data point here, in this case, this is the visit ID of a patient, is linked to the fields, format of the fields, and everything else that you may want to know, the ETL time, the rule for that ETL process. And as you can see, every single data point is stamped with tracing lineage information that would be necessary for quality or audit. The big picture is that as many times that the data exchanges hands before it gets to the semantic data lake here, you can see what was the field, what was the quality of the data at the field, at the source. This is the EMR. This is the interrogation of the EMR before we did the ETL. At this time, how large was the data set, how complete was the data set, what was the last time that this was updated, and then it lands in enterprise data warehouse, the quality of the data at the time that it was landed in the enterprise data warehouse, and this is the data at the semantic data lake. So every single data point is traceable back to the source and the quality of the data at the source, and this is the mechanism that enables building automated quality control facilities that can detect whether or not, for example, ETL pipeline has stopped and you no longer are receiving outpatient diagnoses data or outpatient lab data because something has gone wrong. You can detect those kinds of anomalies and deal with them without waiting for a surprise to happen. And it also accounts for multi-source data. If you are putting data from three fields into one, it traces that too. Some really cool traceability functionality. Any given data point, because of all of those metadata, is traceable to the field that may contain that. So you can take any CPT code, for example, and say, I have a CPT code. I have no idea where can I find this in my enterprise data warehouse. And it can, this is actually basically saying that that CPT code has representation in these two fields within the two tables, two different fields have the same CPT code in our enterprise data warehouse. And the consequence of that is that we can actually create dynamically contain a dictionary and catalog of all information. This basically shows how if you're looking for patient diagnoses, these are the fields that have that information. Procedure date, these are the fields that you can see the procedure date in your system, and this is all harvested automatically rather than someone making a note somewhere. Because of all of those metadata that is linked and which enables automation and scale out, we can ask really interesting questions such as, so what do I know about this patient? Tell me everything there is to know about this patient, the 360-degree view of the patient. This is not probably mind-bogglingly complex use case, but I want you to notice the simplicity of the query and how interesting, how intuitive it is, which we basically say, just count the types of information and group them by type when it comes from this patient. And as you can see, it says I have one indication of a city, 33 patient diagnoses, and as you add more data about this patient, no matter how complex the graph is, to get into these data points, you can actually trace and track and find exactly where the data is for the patient's diagnoses, patient's date of birth, patient's gender, and build mechanisms to retrieve that or quality control that and so forth. This is also one of the key ingredients of our patient engagement approach, where we want to be able to provide reports to the patients on what do we know about them, and how many times this information has been used in different settings. That's basically part of the HIPAA. And we have created infrastructure to be able to, no matter how complex our data infrastructure is, be able to trace and track what do we know about our patients. So that was our knowledge base, metadata, and data management. How this all comes together is that we, of course, we have this knowledge base that we use it for annotations and linkages. We have created a annotation engine. It is also familiar with the notions of time. As I mentioned, we have a specific view of the temporal relationships that we would like to represent so that we can build analytics on top of. This annotation engine takes all of these data sets and annotates links to ontologies that we have, either automatically or using some level of human interaction. This is the software that we have developed to do that. It is very similar to any vanilla ETL software that everyone would be familiar with, how to navigate. And you go through a couple of steps to do the ontology mapping and characterize what are the annotation frameworks we want to use for these data sets, and it does the rest and creates the semantic data lakes graph. The only thing that is necessary for the modeler to know and to be able to operate on is to understand the data at the source. We do not require our modelers to know anything about the technology, about ontologies, about the graph or RDF. We just expect them to know what the data means at the source. The rest is handled by the system using those interactions to have them annotated, and the system does the rest. In the interest of time, because we don't have much time, I will skip some of these slides. Our notion of analytic tapestry, as I mentioned, is basically to link downstream analytic processes to database. So our semantic data lake incorporates data and all of the value-added analysis as well. We have created another software that, again, interacts with users, ask questions about what exactly is it that they want to incorporate in their analytics. What are the transformation methods they want to use, imputations, filter functions, validations that they want to do, how they want to run their analytics in the system, and creates an ontology of that analytic process. And that ontology is one that then ignites another algorithm that can push the information to any analytic framework that is being used: KNIME, H2O, R, Spark, SAS. We don't care. We can push the data. First, find the data from STL, format it the way the user has requested, push it to analytics, and once the results are back, consume it and put it back in the STL. As I mentioned, we can write it into a data mart, so people can do this on their own, iteratively mature their model, but once it is ready, put the results back into the STL, or send it to a service somewhere that does take care of the data analysis, get the results, put that in the STL. So that's basically the framework for analytic tapestry. We have automated the process. We believe that it has turned over semantic data lake from a system of records to a system of insight, because we know everything about patients. I'm going to give you an example of an analytic tapestry query. This query says, for this one patient, tell me what were the analysis that we did for that patient, what were the input to that analysis, and whether or not there was a secondary analysis that took the output of that analytics as an input, what other input was used, What were the secondary analytics, and what did we do with the results of those? Did we send that input somewhere else? I'm just going to show you the results. This shows that there is a 1R score that has been created by a random forest algorithm for a project called Approve. These are the inputs that we've pushed into that random forest. The score was calculated, which was used by another analytic. This is a rule-based analysis, actually. So this rule was fired based on this input and several other inputs of its own at this time, and created a notification. And that notification resulted in creation of a email that has been sent at this time to somebody. I just took one of the data points used to invoke this random forest and show all of the lineage information that you have seen previously. So, and this is the critical aspect of our clinical decision support. When you are sending a note or a page to a doctor that you need to intubate this patient, you better to be able to answer the question of why. Why did you believe that this patient needs intubation? You can really provide all of the data, metadata, and quality information that would convince someone whether or not this is a reliable application. This is basically evidence behind any conclusion that we create in the system, and it helps us with other audits and security and protections. So all of those data points are there. The Approve project is basically the use case that we are validating the Semantic Data Lake. It makes a prediction based on 68,000 training data, 8,000 admissions data set of whether or not patients will die or will need resuscitation, respiratory resuscitation in the next 48 hours. It is highly sensitive and very specific. We have only 1% false positive, and we outperform any published algorithm that do similar things. This is basically a view to our analytic tapestry using 9, which is another analytic framework that we have integrated to SDL. So this is our analytic integrated software that uses the tapestry information to create to query the data, take the frame description, which is what I showed you, an ontology that describes what is the input to this, compile the frame, do the imputations, do all of the new derivatives, run random forests, and the Bayesian analytics that is needed to run. Join and push the basically the results of scoring back into the SDL. That was the version 1. This is the new version of the same analytic for the Approve project. As you can see, we are actually injecting a classifier, and this is all done by frame description. Users just enter that questionnaire. They say, I want to do this, I want to do that. And this analytics are enabled and pushed into the software, and now you can actually create all kinds of new functionality. What we are doing here, we are running 5 different versions of the same model, implemented by different concepts and different perspectives, and we actually compare the results of them at the same time before we use any one of them as our downstream process. This is a process we call superlearner, which looks into results of many decision support systems, logistic regression, random forest techniques, to create one integrated fusion of all of those scores. So you can basically optimize your analytics by comparing multiple versions of the model to find the best prediction rather than going only with one model. We have currently implemented the topological data analysis as part of our tapestry mechanism. So you can actually look into topology, the shape of the data as an indicator for clustering of the data. Again, part of the process, I think. So yes, and these are all graphs that are generated by SDL and the software that is now currently monitoring the performance of our approved process at the hospital level for delivering basically the analytics at the point of care by using all of that information that I just mentioned using SDL framework. I'm going to skip because there are so many. I think we ran out of time. The last slide here is that what I showed you, I hope, is an indication that what we have built and we call Semantic Data Lake is basically motivated by a architectural understanding of what it takes to incrementally mature into a learning healthcare organization by bringing data, metadata, knowledge bases, and linked open data into one unified analytic framework. This is where I think I need to stop.
Thank you, Dr. Mirhaji. We'll take just a few moments for some questions. We have a few queued up here. A couple of questions actually are around the advantages of RDF in particular. Why is RDF critical? Everything that you've talked about here is about analytics. Why is RDF the critical point? What advantages do you see in using RDF over other data representations?
The critical advantage, I mean, other than elegance and simplicity, I think that the notion of ability to link data to metadata, to knowledge, and to the external data sources and doing it in an efficient and in a rich and expressive way is the #1 value add. It is literally impossible to do this if you are not using a graph-based representation. And RDF is a very good way of creating robust graphs. I would say that RDF alone is not enough to do what we are doing. The notion of triples with graph, let's call them quadruples, is not enough to go to this level of representation. For reasons of optimization, scale, and security, we had to add more nodes in our architecture. I didn't even talk about the backend. How the Hadoop/graphics integration works, how the distribution of graphs over multiple machines work. But in order to support all of these, you have to extend the notions of RDF to achieve this level of complexity so you can have many, many different views on top of the same data without having to rewrite it or reformat it every time that your use case changes, which is the second value add. Any other representation, which is not a schema-less, will result in creating many, many silos of data because those use cases will require a different schema and not compatible schema with your original schema. You'll inevitably result in those kinds of silos. That is why I started with the notion of single sourcing this information, because this is one representation that can mold into many, many different representations. That's why we don't call our transformation processes ETL. They are ELT, which means transformation happens as the last step of the way when you are delivering the data to analytics or to application. You just extract and load, no transformation beyond just pure, simple RDF graphs.
Okay, next question. How are you currently using or planning to use this semantic data lake? In other words, what use cases are you first addressing?
So I actually showed you the creating a clinical decision support framework enterprise-wide. The approved algorithm is currently running on entire hospital system, 7 hospitals, all non-pediatric patients, regardless of their point of entry, are being monitored by the approved right now. The same framework is, as we speak, is being applied to do risk scoring for readmission, disease and community-based readmission, very, very granular, basically, way of predicting risk of readmission for the patients, for predicting rupture of aneurysms, for sepsis, for predicting relapse of C. diff, Clostridium difficile. These are really inherently different use cases, but architecturally, framework-wise, data processing-wise, they use exactly the same architecture. We don't really need to create another data mart for sepsis, another data mart for aneurysm, for neurosurgical decision support. We just use the same framework. We just add a frame description and push it to analytics and bring back analytics into the system, and it's now queryable.
Okay, thank you. So next question. An early page mentioned Internet of Things, but I don't think it was, there wasn't much said after that. What linkage is there to Internet of Things other than it's a buzzword for a class of data sources?
Yes, it is. So currently it's exactly that's the buzzword. I said it is based on principle of. I didn't say that we have actually a implementation of that, and I said it is a work in progress. We have seen it as a facilitator to adapt and to align when the technology, when Internet of Things itself evolves beyond the buzzword. And the use cases that we have in mind is by linking it to, by understanding the source of these data points more precisely, so we know what is the device that is being carried by person A and how it is different than person B. What are the differences of different monitoring devices in terms of their resolution, their calibration, their quality, that are generating exact same data about the same patient or categories of patients, and linking that to our decision support algorithms. The scenarios are, yes, basically better understanding of the source and making them dynamically available for analytics, basically in general. The use case that we have in mind to do that is, this is something we are in negotiation with Microsoft to see if we can get some help to integrate their API, is to use bands to collect mobility data and use the mobility data along with some clinical data to create a classification, a mood change and depression classification scheme for patients. So by way of just seeing and comparing their sedentary mobility, pace, not just number of steps, but the pace with which they take steps and the distribution of those steps during the day, we believe that we can, and connecting that to the clinical data, we can actually detect depression.
Interesting. Thank you, Dr. Mirhaji. We have a few more questions. We might have to have briefer answers here in order to finish up in time here. Well, we are over time already, but in order to finish up. Next one is, how is the system more likely to get linkages correct, avoiding false positive and false negative relationships? Especially, there's a worry about patient identity cross-referencing, including improper data as part of a patient data or excluding improperly data that is actually about that patient.
Yes, well, we are using the best of the breed technology to do the linking, which is human curation right now. On top of that, I mean, I'm not claiming that we have done a lot of work in that, but we have created enough metadata to be able to automate some of these things that we know can go wrong or can be detected automatically. One example of those metadata that we are in the planning stages is to create a curation, automated quality framework for our master patient index, where understanding whether or not these are the same people or different people with very similar characteristics is very critical. And we would like to first understand how best we can detect these errors in the mapping. And once we understood, and let's say we merged or unmerged patient information, how we can ensure that the clinical data is also unmerged correctly. This can only be done if you have massive amount of metadata and processes that can actually scale when you're tracing data in multiple places about the same patient and deciding when and which one of those data you want to out or in for specific patients. But we haven't really done much other than just conceptualizing it and having conversations with our business intelligence team to start implementation. So yes, I think we have some breadcrumbs that we have put to find our ways when we want to automate, but currently we have just we are using human annotations, human curation.
Okay, 3 more questions, and I think we're going to have to close it off after that. Next is, what ontologies are you using? Can you mention some of them?
We have a couple of ontologies that we have built on our own. The rest are basically everything that we could get from SNOMED and UMLS. We have reviewed several of the NCBO ontologies. We couldn't really find anything reliable that we could reliably integrate to our platform. But majority of our basically ontologies are the ones that we have created on our own, and some knowledge bases that we have adopted from UMLS. There are all of the 183 terminology systems within UMLS are here. The semantic relations, which is over 2 million relations that OMOP has curated, are here as well. And it is a very rich ontology, if you will, that we are not authoring ourselves. We are just reusing from existing sources. The ontologies that we have built are basically the work product of almost 10 years of research. And they're basically built to not only work with creating linkages within the structured data set, but also in parts of the speech and in clinical text.
Okay. Next question, how many triples are used in total in your data lake, and how many patient records? Or on average, how many triples are used per patient record? And how is
average per patient? I don't know. Our system has 2.8 million patients and I think 12 billion triples. And we haven't really compiled everything. Only those things that we needed to support some of these projects. You have to realize that scalability issue, especially when you're running concurrent queries and you are also in production with some of these algorithms, are real. And so we are trying to not to complicate the world for us. Our next version of the backend, which will be hopefully released by end of the summer, which will optimize the way we partition data, partition graphs, and annotate graphs for security and authorization, so we can do queries much faster, will enable us to compile even more data. And I think we will have something around 100 to 150 billion triples pretty soon. For example, for right now, we don't have any device data in there. We don't have genetic data in there. Not all of the clinical findings, basically the EAV tables, the catch-all tables of our EMRs that people put everything else in there, are compiled into this, and those are the largest sets of data.
Okay. Final question. How do you deal with patient privacy issues in using this data lake?
That is a big narrative that I skipped. We have a dual representation of data. One is date shifted. So we don't really have the actual dates anywhere in the system. We have a unique shift for the patient and the shifted data. If the use case requires actual data, we unshift it and we encrypt everything. And these processes are partly the ones that I'm basically telling you that our next release will optimize. So some of these can be pushed into the backend at the query time. So some of this can be actually part of the multiple nodes that we use for representing any facts. So we can do these at the backend and optimize the process. But our current representation is a dual representation where everything is de-identified and identification happens only just in time when we need it, based on those shifts and unique member IDs.
Okay, great. Well, thank you very much, Dr. Mirhaji, for discussing your work, and thanks to our audience for participating. If you'd like to receive future notices of Yosemite Project events, just visit yosemiteproject.org and click on the link to join our email announcements list. Thank you, everyone, and goodbye for now.